Hi there, welcome back. This is lesson 2 in our organic chem unit. Today we're going to be talking about how to name different hydrocarbons. So yesterday you guys got a intro as to what organic chemistry is and the different types of compounds that are involved. But today we're going to take a closer look at them and name them. This is pretty fun, I think. It looks complicated at first and from afar, but once you actually start thinking about it and breaking it down, like I'll show you, it's not that bad at all. It's a pretty good way to impress people that you know fancy complicated things. Anyway, it looks like there is nothing due tonight. Just make sure that you are following the calendar on the website, as well as any other announcements your teacher may or may not have for you. So what works best for this lesson is for you to look at the note sheet on the website titled Naming and Drawing Hydrocarbons and following along with this video. So just a heads up, there is a lot of practice built into this, so it may come out kind of long, but feel free to skip around as you see fit. Anyway, let's get going. So this is the first yo-yo question. Again, that's what I call a do now if you are not one of my students and you're watching this. So this kind of reviews what we touched on yesterday. What compound is a saturated hydrocarbon? So when we're thinking about it, hydrocarbons, they have hydrogen and carbon only. So that's what the name says. If you have any other element within them, it can still be an organic compound, but it will not be a hydrocarbon because hydrocarbons only have those two things. So knowing that, we can get rid of C and D right off the bat. The second part is looking at what is saturated. So a saturated hydrocarbon is something with all single bonds. So one way I like to remember that is S for saturated, S for single bonds. So looking at these formulas, you're like, well, how do I know which one has a single bond? It might help if you look at the formula kind of all as one piece. So if we rewrite A, we can see it's C2H4, and if we rewrite B, it's C2H6. So that's kind of easier to look into. And so if we're looking for something that's saturated, we're looking for something with single bonds. But without drawing it, how can the formula tell you? And that is where table Q comes into play. So for single bonds, these are your alkanes. And it follows the formula CnH2n plus 2. So N is the number of carbons. So for every carbon you have, there should be double the amount plus 2 hydrogens. So between A and B, B is the only one that fits into that formula. So therefore that is your answer. Number 2, this one says which represents an unsaturated hydrocarbon. So again, hydrocarbon, you have H and C only. And looking at the answer choices, that doesn't really help, but that's okay. And when we're talking about unsaturated, we're talking about something with multiple bonds. And so there are two types of things with multiple bonds. We have double bonds and we have triple bonds. And so those fit into this section of the table. Things with double bonds are called alkenes. They end in ene and have that formula. And then things alkynes with the yne ending have triple bonds and follow this formula. So if we look at the different formulas given, we can see, might take some time, but A fits into the double bond formula. It fits into that one right there. B, C, and D all fit into the single bond alkane formula. So that means A has to be the answer. Moving forward with the last one. This one says, what is the general formula of this compound? So again, you have thank you, passing by motorcycle. I appreciate that. Okay. So here you're given a condensed formula. So you can do this a few ways. The easiest way is just to kind of rewrite the formula as a molecular formula, so you can just look at the number of pieces. And so that would be C4H6. And with that, you can look at, okay, now which formula does this fit into? And you'll see that it fits into C. So what that means, so 4 is the number of carbons. So if we plug in 4 for N, and then 2 times 4 is 8, minus 2 is 6. So that tells us it is an alkyne. If you wanted to, you could also take this condensed formula and draw the structure of it, and it would look like this, where that triple bond would be right there. These are H's. And if we think back to how condensed formulas were written yesterday, break it up for each carbon aspect of it, and it matches. So either way, however you find the formula is fine, as long as you can figure out that the answer is C. Okay, so moving forward, we are going to talk about how to name these things. We're going to break them down by the different classes. So straight chain alkanes, straight chain alkenes, straight chain alkynes, and then alkanes with branches. So a lot to cover today, but it will be kind of a lot of fun because there's a lot of drawing. I personally really like this. So straight chain alkanes, you can see that it's already circled. Anything that ends in an A and E ending has only single bonds. So we're going to need a few things to help us name. Table P, which looks like this, gives you the prefix, so the beginning of the word. This is how the word starts. And depending on the prefix, tells you how many carbons are there. And then, because we're talking about alkanes, we have to use that A and E ending. And that is what table Q is for. So P tells you the prefix, Q tells you the ending. So I think we covered a few of these yesterday, but let's just kind of jump into this. So, first example is pentane. We always want to focus on the carbon chain first. So pent means 5 carbons. So we can go 1, 2, 3, 4, 5. And then ane means you have single bonds between those carbons, just like that. And then everything else is an H, just like this. So this is one of the easiest things to draw. And that's it. Now, if you wanted to, you could have done the chemical formula first. We know it's ane, so we know we have to fit into the alkane family. We know there's 5 carbons because of pent. And if we plug into the 2n plus 2 formula to get the number of H's, 5 times 2 is 10, plus 2 is 12. And so your chemical formula would be C5H12. Now, if it helps you to go from chemical formula to structural formula first, that's fine. If you want, the order doesn't matter as to which one you do first. If you wanted to double check yourself, both of these things should have the same thing. So you can see 5 carbons and 12 H's. Okay, next one is butane. So bute, again, that is bute, not but, means you have 4 carbons. 1, 2, 3, 4. And then ane means you have single bonds between those carbons, just like that. And then, as of right now, we haven't mentioned anything else more complicated. So everything gets an H. Now, if you notice, I just made the little line leading towards the H, but didn't actually draw the H. This is totally okay. If we drew every single H every single time, we would be here a very, very long time. So this is a perfectly good way of writing it. The fact that you have this line coming off of it shows that an H will be coming off. It's kind of like the invisible ones when you're balancing reactions. You know it's there even though you don't write it. Now if an element it only works for hydrogens. Those are kind of invisible when we talk about organic compounds. If it's any other element, they will be drawn. But having it like this is fine. And then the formula is C4. And then again, we're plugging into the alkane formula. We can also count the H's that are kind of hiding. And you get 4 times 2 is 8 plus 2 is 10 as your chemical formula. And that's it. So, continuing with alkanes. So, we're still just talking about things with single bonds, or alkanes with branches. So, as you can see, this picture looks a lot more complicated because now there's like things hanging off of it. And that's what a branch is. So, if you're like, well, how do I know if something's a branch? You can kind of trace over the compound with your finger, and if you can't touch all the carbons without picking up your finger, then it's a branch. So what I mean by that, if we start here and then follow this path, I touched 4 carbons, but there's still part of it that I haven't highlighted. If I follow, this path going up, that's fine, but there's still carbons I'm not touching. If we go this way, there are carbons we're not touching. So we can see that there are branches. So when they're naming them, and here are some more examples, these names look more complicated. But again, if we break it down, look at it piece by piece by piece, it's a lot simpler. So these names are essentially directions as to how to draw these compounds. So before we even get into drawing them, we have to talk about what the branches may be. So generally what you'll see at this level are 2 types of branches, a methyl group or an ethyl group. Now you can have longer branches, but this is just to kind of keep things, and they work the same way, but to keep things kind of simplistic enough for now, we're just going to stick with methyl and ethyl groups. So if you think back to table P, methyl means 1 carbon. So a methyl group looks like this, and it's attached somewhere off your compound. So this is your compound. So you have CH3 attached to something. An ethyl group, so remember table P has ethyl as 2 carbons, looks like this. So that 2 carbon chain attached to your compound. So it would be CH3, CH2 attached to something. So those are generally the groups that you'll be seeing. And we'll work through how to place them and how to name them. So this slide gives you a long list of how to name these branched alkanes. I'm not going to read this all to you because you guys are very capable of reading. But just to kind of point out a few things. The most important thing is finding the longest possible chain. So when we go through a few examples, I'll show you what that means, but we're not just looking at these compounds left to right. Remember, these are 3-dimensional objects. So if I'm holding something, like pretend we're in the classroom, if I'm holding something and it looks one way to me, it will look mirror image to you. And that's totally okay. But when we're naming them, we have to take this into account. The branch names comes first, and we use the YL suffix, which again, this will make more sense when we actually do an example. And then you name the parent chain. So let's jump into this. This first compound isn't actually a branch. This is a kind of condensed formula to show 1, 2, 3, 4, 5, 6. To show this 3, 4, 5, 6. To show this compound. So if we're going to name this, to kind of quick recap from what we were doing before, longest carbon chain, there is only 1 possible chain, and there are 6 carbons, which means we have to use the prefix hex. And then in between those carbons, we have all single bonds, and we use the suffix, or the ending, ane. So this is just your plain basic hexane. Now, this example is when we have branches. So there's a few ways we could look at this. If we look at it in this blue highlighted section, we have 4 carbons in that chain. Okay, it could be the longest one. It could not be. Let's keep looking. If we look at this purple one, there is also 4 carbons. Now, just to show you the last option, there is that green path, which has 3 carbons. So if we're doing this, then we have to use the longest chain. We can't use the green path. So then you're like, well, do I use the purple one or the blue one? And the answer is, it doesn't matter. They both have the same name. So just because the purple chain turns doesn't mean that you can't use it as the longest chain. So let's use, to match up with what I did on the answer key, this blue circle. So in that longest chain, you have 4 carbons, and you name 4 carbons with but, again, not but. And then in between those carbons, we have all single bonds, so you name that butane. Now, as of right now, we have the name for what is in that blue circle, but we can't forget about that branch. So the branch with 1 carbon is meth, and you always add that YL ending for the branch. So methyl butane. Now this last step is you have to kind of give the address as to where this branch lives. So if you were to think about it like this, each carbon has to be numbered. So in that longest parent chain, you have to, solidify a starting location. So if I label my carbons left to right, it's like what I wrote in black. But it is possible to label your carbons right to left. So right to left, left to right doesn't really exist when we're talking about these organic compounds. So if you'll notice, depending on how I label it, it gives the methyl group on the second carbon. But if you number it the other way, it says the methyl group is on the third carbon. And you might be asking yourself, well, does this matter? And the answer is yes. So in that long wall of text on the original instructions, you have to name the branch on the smallest carbon, the smallest number. So this does take kind of some playing around, but the smallest number is what's smaller than which one is smaller, 2 or 3? Hopefully everyone said 2. So 2-methyl butane. So again, kind of break down this name. But means that longest chain has 4 carbons, so that's this. Ane means between those chains you have single bonds. Methyl means you have a CH3 group somewhere, and then that 2 tells you where that CH3 actually is. So the name is kind of a map as to, or instructions to how to build this compound. Okay, moving forward, we have this compound. So this looks pretty complicated. It's not as bad as you think. So our first step is to find the longest chain. So this will take some kind of trial and error to find that. So let's see. If we start here and highlight in yellow, that is 1, 2, 3, 4, 5 carbons long. Okay. Let's see if we can find a longer chain. If we go 1, 2, 3, 4, 5, 6, that worked. That's longer than 5. So now we know we can't use the yellow line. Let's see if we can find a longer one. 1, 2, 3, 4, 5, 6. So green is also 6 carbons long. So at this point, it doesn't matter if we use the green or the blue one, because it will have the same thing. So just to keep things uniform with the answer key, let's use the green path right there. So we had said that the longest chain was 6 carbons, and so to name 6 carbons, you write hex. And then between those carbons we have single bonds, so we have ane. Now in terms of what you're going to be seeing, all of the compounds with branches will be alkane, so things with the chain will have all single bonds. So the other compounds do exist, you just won't see them as of right now. Okay, so your parent chain will always have that ane ending for what you're seeing now. So now we've named everything in green. We have to name now that branch. So that branch has 2 carbons in it, and that is your ethyl group. Remember, F means 2 carbons, and YL is the ending you give to the branch name. But now we have to give the location of that ethyl group. So here comes numbering the parent chain. So if I label it in green, I start numbering this way. 1, 2, 3, 4, 5, 6. It looks like that ethyl group is on carbon 4. But let's just double check the other way to make sure that it is on the lowest number. If we label it oppositely, 1, 2, 3, 4, 5, 6. Well, now the branch is off carbon number 3. So when you have this disparity, when you don't know if it's 3 or 4, scientists were like, okay, instead of driving everybody nuts, let's just use the smallest number. And what's smaller, 3 or 4? Hopefully you all say 3. And so that is 3-ethyl hexane. Again, it looks really, really complicated, but if you just kind of think about it, it's not that bad. I always really liked this and thought it was it's like a puzzle. Okay. Last one in this section for right now is 2-methyl pen. No, not last one, sorry. First one of giving me the name and then having to draw it. So let's start off complicated. We have 4-ethyl heptane. So when you're going from name to picture, your first thing should be looking at finding the parent chain. And so that's what this heptane is. So hept means 7 carbons, and ane means you have single bonds between them all. So 7 carbons. 1, 2, 3, 4, 5, 6, 7. Okay. And then we'll add the we can always add the H's last. So now we have to add this ethyl group. So remember, ethyl looks like this. Here's your compound with all of your H's. But the question is, where do we put that group? And the answer is on carbon number 4. So when we label them, 1, 2, 3, 4, 5, 6, 7, like that, carbon number 4 is this one. So off of that, then you have your ethyl group. Now at this point, everything else can be filled in with H's. Remember, when we're talking about these alkanes, they're saturated, so you have to have everything else is filled in with H's. Carbon can make 4 bonds, so carbon always has to have 4 lines coming off. And that's pretty much it. The answer key that I posted online does have all the H's drawn in. If I spend drawing every H, this video will be twice as long that it needs to be. Okay. Next question. Let's draw 2-methylbutane. Again, you want to focus on the parent chain first, and that's what I boxed in green. And bute is 4 carbons. So we have 1, 2, 3, 4 carbons. Ane means you have single bonds between those carbons. And then you have a methyl group, which is that CH3 somewhere. And the question is where. So if we label the carbons 1, 2, 3, 4, we can add that methyl group right here on carbon number 2. And so everything else is an H, and it looks just like that. Now, this is the same thing as if I wrote it like this. 1, 2, 3, 4. Drawing it like that. So here, it technically looks like this branch is on carbon number 3. But remember, we can label them left, right, or right to left. Both of these things are the exact same thing. Okay. Now the last one for this section is drawing 2-methylpentane. So again, we're following the same protocol. Pentane Pent is 5 carbons. 1, 2, 3, 4, 5. Ane means you have the single bonds between them. And again, we'll add the H's last. And we have a methyl group somewhere. The question is where. And the answer is on carbon number 2. So let's add that methyl group right there. And then you can go ahead and fill everything else with those H's. That is perfectly fine. If you drew it like this, 1, 2, 3, 4, 5. That's also fine as well. And if you drew a top or bottom, that literally doesn't mean anything. Okay. So, that's it for alkanes, branches or straights, anything with single bonds. Next, we're going to talk about alkenes. Those are things with double bonds. And so anything that has the ending E-N-E tells you that it has a double bond. And then we're going to be talking about that section on table Q. So it follows a slightly different general formula and ends in that E-N-E and has that double bond. So we're still going to use table P for the prefix, so the start of the word, to tell you how many carbons are there. But now we're going to add on that E-N-E ending to show that you have a double bond somewhere. So let's get started with this one. It follows the same kind of protocol we use for naming. You want to name your longest carbon chain first. And here we only have one chain, so every chain will be the longest chain when we're naming alkenes for right now. So we have 5 carbons. How do you say 5 carbons? Hopefully you're all shouting out pent into your computer screens. Sometimes I feel like Dora the Explorer, where she asks these questions and nobody's there to answer them. Definitely a very weird scenario. Okay. Anyway, keeping things interesting, we can see that we have a double bond right there. And so, now we use the E-N-E ending. But, because these double bonds can be located in different spots, we have to give the location as to where the double bond starts. So, we have to label the carbons just like we did when we were talking about branches. And you don't actually have to physically number them, but you have to at least number them in your head. So, if we label them in red, left to right, or if we label them in orange, 1, 2, 3, 4, 5, right to left, we have to again make sure we're starting on the smallest carbon. So if we're looking at the red example, it starts at 2 and goes to 3. If you look at the other way, it starts at 3 and goes to 4. So again, we want to write the smallest number, so that's going to be this section. And then you have to give that number as to where that double bond starts. So it would be 2 pentene. So pent because of the 5 carbons, ene because there is a double bond somewhere, and then 2 tells you where that double bond starts. Okay, next one. We want to name the carbon chain first, so we have 3 of them, and that is prop. Now we have this double bond, so we have to give it the term ene. But now the question comes into where is that double bond located? And if we label our carbons left to right or right to left, we want to make sure we are using the smallest number to show where that double bond starts. And so if we go left to right, starting at 1 is the smallest number. So 1 propene. Prop because you have 3 carbons, ene because there's a double bond somewhere, and number 1 tells you that that double bond starts on carbon number 1. Hopefully you guys are starting to get the hang of this as we're moving forward with this. Okay. Next, gave you the name, and I want the picture. So, again, we're going to follow the same thing we've been following so far. Let's draw this parent chain first, and then add everything else that needs to be added in. So, we have hex. Hex means 6 carbons. 1, 2, 3, 4, 5, 6. Now, we can connect them all with a single bond, but this ene tells us there is a double bond somewhere. The question, though, is where? And the answer is right there. So that 3 tells us where the double bond starts, and it's telling you it starts on carbon number 3. So if we label them 1, 2, 3, 4, 5, 6, carbon 3 has that double bond right there. So that is where it belongs. And then everything else can be filled in with H's. Now remember, carbon can only have 4 lines coming off of it. So that is why you do it in blue. Notice I did not put lines there to show H's, because that would be too many things. These carbons have 4 lines coming off of it. So that's what makes these multiple bonds, these double or triple bonds, unsaturated. Because there is the potential for room for these extra H's to attach, but right now the bonds are being used in other locations. So it's okay if you have this little empty section. That is totally normal. And again, if you drew it like that, that is fine. If you put your extra H's on the bottom, that is fine too. That literally does not change anything. Okay, decene, for decene. I apologize in advance for this obnoxious compound. You might be asking why. Well, dec means 10 carbons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Again, you can go ahead and connect all of them with that single bond. But we're not done there. Ene tells you have a double bond somewhere. The question is where. And carbon number 4 is your answer. So let's just, for this example, start labeling on the right side. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Remember, it doesn't matter which way you start labeling, as long as you're consistent throughout the drawing process. So think on the answer key I have it the opposite way. This is just to show you that it can be done both ways. So carbon number 4 is right here. So the double bond starts at 4 and goes to 5. Now, you can add in your H's everywhere else. Again, I'm not going to draw every single actual letter H in. So I do not want to be here forever, and neither do you. And there you go. That is your 4-decene. Okay. Lastly is straight chain alkynes. And here we have that Y-N-E ending. And so we're going to be focusing on this section of table Q. And so anything with a triple bond ends in Y-N-E or on. So I haven't given these to you in a while. Here is a lovely meme going over this. Organic chem is difficult. Those who study it have all kinds of trouble. So you probably just groaned your computer to yourself or laughed out loud. Either way, you're welcome for that. It's so much different not getting these weird groans and eye rolls in person, but I believe you guys, you did that. Anyway, going into this, so let's work on this structure and then figure out what its name is. So just like everything we've done so far, your first step is to name the chain. So we have 1, 2, 3, 4, 5, 6 carbons. And so what do we name 6 carbons? Hex. Okay. Now we have this triple bond. So according to table Q, when we name things with triple bonds, we have to use the Y-N-E ending, the ine ending. And then we have to give the location, just like with the double bond, as to where this triple bond starts. So if we label it in red, left to right, 1, 2, 3, 4, 5, 6, we can see that the double bond starts on carbon 3. But if we label it in orange, the opposite way, 1, 2, 3, 4, 5, 6, it also starts on carbon number 3. So here it doesn't matter which way you start labeling it, but it's always good practice to kind of get in the hang of looking both ways. So we can say 3 hexine. Again, hex because there's 6 carbons. Ine because there's a triple bond somewhere, and then where does that triple bond start? The answer is carbon number 3. Okay, next one is here is another lovely structural formula. Let's name this. So first step is naming the carbon chain. There are 4 carbons, and so we use bute, which is not but, it is bute. And then we have this triple bond, so we name it Y and E at the end. And then we gotta, tell the world where this triple bond lives. And so if we label it 1, 2, 3, 4, or 1, 2, 3, 4, it can start on either carbon 3 or carbon 1. And again, we have to use the smallest number, so it would be 1 butane. One of the other reasons I love this unit so much is that when you guys are saying, and the names get a little bit more complicated later on this week, but having you guys actually say these out loud, it's like learning a different language. It's quite funny. Okay, next, here is the name. Let's draw it. It is 2-pentyne. So, our first step should be to draw that chain. So, pent is 5 carbons. 1, 2, 3, 4, 5. And you can go ahead and connect them all with a single bond. But we're not done. We have an ine to take care of. So we have a double bond somewhere, triple bond rather, somewhere. Question is where? And the answer is 2, on that, starting on that second carbon. So let's kind of label it backwards, just so you guys can see it both ways. So this way, and then how I have it on the enter key. Again, it doesn't matter. Starting on carbon 2, you have that triple bond right there. And then you can go ahead and add in your H's. Oops. Now, see what I did here? In this section, right now, there's a mistake. It looks like I have 5 lines. Hold on. Erase this. The way I drew this carbon has 6 lines coming off of it. That is not okay. That is a mistake on my end that I did on purpose to show you guys. So, if we erase this green box and erase these 2 H's, now carbon has 4 lines coming off it, and that is good. And then like that. So when you have a triple bond in your compound, it does give a kind of very straight section to it, which is absolutely normal. Okay, I think this is the last example before we jump into a few practice questions to wrap everything up. 3-heptyne. So hept, 7 carbons. 1, 2, 3, 4, 5, 6, 7. And you can go ahead and add those single bonds. Then we have to add this triple bond. Question is where? Well, it starts on carbon number 3. So let's go 1, 2, 3. Add that triple bond. And then go ahead and add all of your H's everywhere else. And boom, that is your 3-heptyne. So, that is it for right now. There are 4 egregious questions I want to quickly go over with you. And that is it for today. So if you've been watching this since the beginning, good job. I know this has been a long one, and I'm trying not to make it as boring, but it is a lot. So jumping into this is a long question with a picture. I am not going to read all the question for you because you guys are very capable of reading. But what I put in bold is what we need. To explain in terms of bonding why the hydrocarbon 2-methylpropane is saturated. So it's saying, why is that saturated? And you all in terms of bonding. So based on bonds, why is that saturated? You can say only single bonds are present. So if you had anything other than single bonds, it wouldn't be saturated. That's it. Similar question, different picture, same essentially question. Explain in terms of carbon-carbon bonds, why is this hydrocarbon saturated? Again, you can say single bonds only. And that's 100% acceptable. Remember, single bond, saturated go hand in hand. Next is more words, gives you a lovely reaction. And goes, write the name of the homologous series to which the hydrocarbon belongs. So in this formula, you'll see 3 different compounds, but it's asking you about the hydrocarbon. That's your key to look at a specific one. So remember, hydrocarbons have H and C only. So it can't be this one, and it can't be this one, because those two have BRs. So we need to look at this compound. So now it's like, well, what's the name of the homologous series? This sounds complicated, nothing you need to memorize. It's table Q. Is it an alkane with single bonds? Is it an alkene with double bonds? Or is it an alkyne with triple bonds? And you shall see there is a double bond, which makes it an alkene. And that's all you needed for your answer. Bunch of stuff just for a one word, simple answer. And lastly, this question gives you a lovely backstory on gasoline. Should you want to read it, go ahead. But the only thing that we need is drawing 2,2-trimethylpentane. So this is an older question, but I want to include it at the end because it does give you guys that nice extra challenge. So it looks kind of scary, but we'll break it down step by step, and it is actually very, very manageable. So let's jump into this. Our first thing should be this pentane. So our 5 carbon with all single bonds. Now, here we have trimethyl. So that means we have 3 methyl groups. So we have CH3 3 times. And the question is, well, where are all those methyl groups located? At carbon 2, at carbon 2, and at carbon 4. So let's start numbering this way. 1, 2, 3, 4, 5. So on carbon 2, you need a methyl group and another methyl group. So those are 2 methyl groups, both on carbon 2. That's how that would look. And then on carbon 4, you have that 3rd methyl group. So it doesn't matter if you put this one on the bottom or the top, it doesn't matter. And then you can fill in your H's everywhere else. And that is your 2,2-trimethylpentane. Again, it seems really complicated, but if this makes sense, you can be like, oh my god, mom, dad, sister, brother, fish, frog, somebody, look at what I can draw. And then you could teach it to them. And then they could be like so amazed by your organic chemistry knowledge. So that is it for this lesson. If you have any questions, let me or your chem teacher know. Again, make sure you are following the schedule for Castle Learnings. And that is it. Have a wonderful day.